Welcome back to Math with Tan. Let us look at a radical equation. One side of this equation is squared. The other side has a square root. They do not look related at all. Square everything to remove the root, and you get a degree 4 polynomial that still has a square root buried inside it. That is not a typo. That is just how ugly this gets. But hidden inside this equation is a perfect, secret symmetry. Two new variables turn this mess into a system so clean, it practically solves itself. Before anything else, there is a square root here, so whatever is underneath it cannot be negative. That gives us our baseline domain. X must be 0 or greater. Keep this in mind. We will layer more conditions on top of it soon. Here is the key move. Let y equal the square root of x, squaring both sides. Y squared equals x. Now let u equal x minus 3. Rearranged, that is u plus 3 equals x. Notice something. Both y squared and u plus 3 are equal to the exact same thing, x. So they must equal each other. Y squared equals u plus 3. That is our first equation. Now go back to the original equation and substitute in u and y directly. U squared equals y plus 3. Look at these two equations together. Swap y and u in the first equation, and you get exactly the second one. This is a textbook symmetric system, and symmetric systems have a standard move. Subtract the two equations. The plus 3 terms cancel immediately. What is left? Y squared minus u squared equals u minus y. Factor the left side as a difference of squares. Flip the sign on the right. Now both sides share the exact same factor, y minus u. Bring everything to one side, factor out that shared piece, and we get y minus u times y plus u plus 1 equals 0. Two cases. Either y equals u, or y plus u plus 1 equals 0. Let us solve each one. Case 1. Y equals u. Translating back, that is root x equals x minus 3. Since a square root can never be negative, the right side must be non-negative too. That forces x to be at least 3. Square both sides to clear the root. Expanding and simplifying gives us x squared minus 7x plus 9 equals 0. This does not factor nicely, so the quadratic formula gives us x equals 7 plus or minus root 13 over 2. Check both against our condition, x at least 3. The smaller root fails the condition. It is rejected as extraneous. The larger root clears the bar. 7 plus root 13 over 2 is accepted. Case 2. Y plus u plus 1 equals 0. Substituting back and simplifying, we get root x equals 2 minus x. Again, the right side cannot be negative. So this time, x must be at most 2. Square both sides. This one simplifies to x squared minus 5x plus 4 equals 0. And this one factors beautifully. X minus 1 times x minus 4, giving us x equals 1 or x equals 4. Check against our condition. X at most 2. X equals 4 fails immediately. Rejected. X equals 1 satisfies the condition perfectly. Accepted. 2 roots survive out of 4 candidates. Quick check with x equals 1. 1 minus 3 squared is 4. Root 1 plus 3 is also 4. It checks out. So the complete solution set is exactly 2 real numbers. 1 and 7 plus root 13 over 2. The lesson is not just this equation. Whenever a radical equation secretly hides 2 expressions that both equal x, try naming them separately. If the resulting system is symmetric, subtracting it almost always factors beautifully. That is the whole trick. Thank you for learning with Math with Tan. See you in the next proof.